Hi, everybody. My name's John Handler. I'm a solutions architect with AWS, and I focus on Amazon OpenSearch Service. Today, we're going to dive into multi-tenant solutions on Amazon OpenSearch Service. Multi-tenancy is a fascinating and really broad topic that touches almost all of your usage of Amazon OpenSearch Service. And we're going to go into a lot of details around data design, performance, security, capacity planning, to really kind of try to paint the overall picture and help you understand what are the best ways to work with Amazon OpenSearch Service when you have multiple data sets, multiple tenants, multiple logs, and all of those need to come to the same place. So for those of you not familiar, Amazon OpenSearch Service is a managed service that makes it easy to deploy, operate, and scale OpenSearch along with a legacy Elasticsearch clusters in the AWS cloud. And we'll get into exactly what OpenSearch does, but we'll take a quick detour and just talk a little bit about what is OpenSearch. OpenSearch is a community-driven, open source search and analytics suite, and it's derived from the Apache 2 licensed Elasticsearch 7.10.2 and Kibana 7.10.2 projects. It consists of a search engine, which is OpenSearch, that provides you the means for searching your data and analyzing your logs. And it has a visualization interface, which is called OpenSearch Dashboards, which you can use to visualize and analyze log data and other streaming data. There are also a set of plugins that OpenSearch provides that add functionality that enable you to do things like generate alerts on your log data, look for anomalies in your streaming log data, bring machine learned models in for search relevance and ranking, interact with SQL, secure your data within your cluster, and much, much more. So I encourage everybody to go check it out. So why would you want to use OpenSearch? Well, first of all, it's 100% open source. So all of the OpenSearch project is Apache 2.0 licensed. You are free to use, modify, and monetize on our code base. It's built in the open, and our roadmap is out there. We encourage everybody to come and contribute to the roadmap, to contribute code to the project itself. And we don't require a contributor license agreement. So all of that code goes right into the project. It is community driven. It's important. We're very committed to open source itself. We really want your input. You should go check out our roadmap. You should file issues and get involved, because we're looking to build a really solid community around OpenSearch itself. It is full featured, so we have our full text search, analytics, ingest, fast ingest, machine learning plugins, security. I mentioned a number of these in terms of the plugins that we offer. Again, I encourage everybody to go check out the open source project and to see what's going on there. So what is it that OpenSearch is used for? Well, there are two fundamental workloads. The first of those is related to streaming data, and a lot of that data is coming from machine-generated sources. Things like your applications and your infrastructure are generating logs at voluminous rates. I think 44 zettabytes is the last estimate that I heard in terms of what we have. That's a lot of data. And it's coming again from your services, your microservices, your web applications are maybe sending in click data or interaction data. Your business applications are monitoring what's going on, and you want to be able to analyze and look at that data. Even your APIs potentially are generating log data that you want to have a look at. In the IT space, your databases, your load balancers, all your networking, your servers, all of these are creating, again, voluminous log data. And that data really contains the information that you need to understand in the IT and DevOps space how your infrastructure is performing. Are there any current problems there? Where do you need to dig in to figure out what's going on with your production deployments? And the last space is in the IoT and wireless. We see tons of data coming in from automotive sources, your devices at home, manufacturing, hardware and software, even mobile applications are bringing in data in the IoT space. And again, this data contains the critical information that you need to make your business decisions and to find out what's going on with your applications, your infrastructure, your security. With Amazon OpenSearch Service, you can bring that data into the service and build out visualizations and dashboards that enable you to dig in and pull out those critical pieces of information that are going to guide you. The second set of workloads that we have are related to search. So the search application is really to take a catalog of information, send it to the search engine, and then provide near real-time search results that are relevant and you can apply to the problem at hand. For instance, e-commerce is a very typical example. In an e-commerce workload, you have a catalog of data. You're going to send that catalog to OpenSearch Service, and then you're going to use the query APIs to allow your customers to come and find the products that they want to purchase. Another set of search workloads relates to document portals. If you have an application that's curating a large set of documents, then you're going to send either metadata for those documents, or you're going to send the content of those documents to Amazon OpenSearch Service to enable you to search for and find the relevant information. Along with search itself, you also want to be able to deliver recommendations to your end users, your customers. Again, in an e-commerce scenario, you want to be able to tell your customer that people who bought this also bought that, people who looked at this also looked at that. You're a real fan of X brand of, say, sneakers. Well, okay, so you probably should look at this particular sneaker, what have you. You also want to make sure that you maintain an easy to use and very fast search experience that's going to enable your customers to bring that information back in near real time and be able to act on that quickly. So these are the general workloads that we see with Amazon OpenSearch Service. And if we look at how the service itself works, we have our two workloads here. We have our server logs, application networking, all the logging data on the one hand. We also have our application data on the other hand, so logging and search. You're going to use APIs. First, you format that data as JSON, and you're going to use APIs to send that data to Amazon OpenSearch Service. There are many different architectures and pathways to bring that data in, but ultimately, you're going to call an API that's going to deliver those JSON documents to Amazon OpenSearch Service. The service itself will then create indexes on all of the fields that are in your JSON documents. Those fields then will be searchable, whether they're full text or string matches or numeric ranges. You'll be able to search across all of the data that's in those search documents. On the other end, you have your users, your analysts, your DevOps, security folks. They're going to use REST APIs or OpenSearch dashboards to pull results out of Amazon OpenSearch Service. So the interaction model is fairly clear. It's really straightforward. OpenSearch itself sits in the databases world. It is very much a database kind of interaction. So turning to our topic today, let's talk a little bit about the basics of tenancy. So what do we mean by tenancy? What is tenancy? If we think about search workloads on the one hand, we potentially are bringing data in from, say, a number of customers. So if I run an application that is vending out some kind of, I don't know, note-taking app or what have you, then I'm going to have a number of customers. All of those customers are going to have notes. They're going to want to search them. So we're going to bring all of those into Amazon OpenSearch Service. On the logging side, we have different log sources. We have system logs, you have web logs, you have IoT data. All of that data is going to come to Amazon OpenSearch Service. You can view Amazon OpenSearch Service as a container. And the container in this case is holding customers or log data, right? But there are actually many different levels of this. So OpenSearch has containers at those different levels. When we talk about tenant, a tenant is a member of a container. In the search workload, it would be one of the customers. In the logs workload, it'd be one of the log files. So some of the containers that we have document containers, so documents contain fields. We have index containers, so indexes contain documents. And we have cluster containers, clusters contain indices. Generally, we would see search workloads spanning different data sets, and usually we would use the index as a container for that. Depending, sometimes you could have a document that has multiple containers in it. Sometimes you have a cluster with multiple indices in it, and that's the container. For logs workloads, it's more typically the index, which is the container, and we're rolling multiple indexes into Amazon OpenSearch Service and working with those. So there are different tenancy strategies. Like at each of these levels, if you think about documents or indexes or clusters as containers per se, then you can have a siloed strategy where each tenant is one-to-one with a container that holds that tenant. In the search workload, then each of the customers there would be a single index if index was the container. There's also a pooled strategy where you take multiple of your elements, whether it's customer or log files, and you combine those and put them into a single container. And then finally, you have hybrid strategies where you want to take some portion of your tenants and put them in one container, and some portion of your tenants and put them in a second container. And how you split them out, generally speaking, is along size and usage lines, so that when tenants get really big, you manage them independently. So we have all of these different strategies for managing tenants. So let's talk a little bit about the data design and how that plays out at the document, index, and cluster level. A good example is multilingual search. So if we look at document level tenancy and we think about siloed workloads, right? If you have a multilingual search use case, say English, French, and German, you can use a single index per language, right? So then I have my English index, my French index, and my German index. This gives you the benefit of isolating these languages for analysis and relevance purposes. If I know that my language is English, I can run English analysis over all of my text, and it's simpler that way. It also maximizes the separations of concerns. You could, at a different level, split out those indexes across different domains, Amazon OpenSearch Service domains, to scale independently and to ensure that if one of those indexes is not available, the others are still up. However, if you're putting all of these into the same cluster, it can be challenging to scale, especially if you have different usage patterns for these different languages. Looking at a pooled example of multi-tenancy, at a document level, you could bring everything into a single document. In that case, you would use a field per language. So I have my English description, my French description, my German description, field. Again, I can apply analysis differentially to each of those fields. It does still allow that targeted language analysis, and putting them into different fields does reduce the relevance effects of between the languages. It does make it more complex to query. You need to figure out then, before you send the query, which language you need to query, and which field you need to query. And it can also make your indices larger just through having to support multiple different languages. Again, at the document level, a hybrid strategy would bring in the individual language fields and then use a copy field that has all of the languages. This can reduce complexity in querying where you may not know what language the query is in, so you can run it against the every language field. You can also target specific fields if you need to. The composite field then would help you with retrieval, but you would have cross-language effects for relevance. In Amazon OpenSearch Service, relevance baseline is computed with something called TF-IDF, and that looks at the distribution of words within a particular field relative to the query itself. So if you have all of these languages going to the same field, you'll have terms that are common across languages that can really affect the relevance calculation itself. So there's some trade-offs here as well. Looking at logs workloads, a pooled logs example is a pooled log strategy is a very common strategy. You're going to manage your lifecycle with a logs workload. You generally manage your lifecycle by writing daily to an index. We'll talk about rolling over at different sizes instead in a little bit. You collect all of those indices in a single domain, and you'll use index level access to visualize different data streams. As you work with this, you may find that the cross-index, there's cross-index contention for the underlying resources. So in some cases, you may go to more siloed strategy where you create a single domain for each data stream. And if you have to query your entire data set, you can use Amazon OpenSearch Service's cross-cluster search to search across all the data. There's some benefits of doing it this way as well. It does reduce your blast radius. So should one of those domains go down, you maintain access to your other data sets. And it does allow you to scale individually. There can be a cost benefit here as well. In a pooled strategy, you may find that you have to scale much larger aggregate to be able to handle the contention that we were talking about, where if you individually deploy domains, you can scale each domain precisely for the resources it needs, and that may give you a cost benefit. So you can also use a pooled logs index. This one is less common, I would say, but you can use a metadata envelope to gather non-workload specific information and then use filters on that information when you're searching or visualizing that data. So if I know my source is syslogs, I can add a filter to my OpenSearch dashboard's dashboard to simply pull from that data source. And this one works fine. Generally speaking, putting stuff together and overall reducing the contention gets you a lot of performance benefit. We'll go into that in a second. And let's talk about the basics. So when you use Amazon OpenSearch Service, you deploy what we call a domain. A domain, as you can see, wraps hardware and software that delivers OpenSearch to you over an endpoint. The resources that you deploy are nodes, EC2 instances. You tell us what to configure and we go do it. We have data nodes. The data nodes are responsible for holding the data and responding to indexing and query requests. So data nodes are your fundamental resource that you're using. We also have a feature called UltraWarm that enables you to move older data into a lower cost storage tier, reducing your overall cost by typically in the neighborhood of 40 to 50% for older log data that's infrequently accessed. Finally, you have a set of leader nodes. The leader nodes are going to provide stability for the cluster. They maintain the state of the cluster and they keep it operational. In front of that, we give you load balancing. We have security integrations with IAM, Cognito, and SAML providers. These are for dashboards login, and some integrations with CloudWatch and CloudTrail for monitoring. And on the input side, Kinesis Data Firehose, Database Migration Service, et cetera, to enable you to get data in. But the core resources that you have to work with are the data nodes that you have. So how is it that the data itself is distributed across those nodes? When you work with OpenSearch, you use indexes. An index is a collection of documents. And as you've seen, the documents then are individual log lines or they're items from your e-commerce catalog or what have you. If we look at a logs workload, and we have two sources here. We have 3 servers. They're sending syslogs and web logs. Those are going to go to a particular index. So an example would be something like syslogs 2022-0208 or weblogs 2022-0208. This is typical to manage lifecycle by day. OpenSearch, you'll define a partitioning of that data. And you'll define a shard count. Each shard is one partition of the data. So if I define 5 primary shards, that is, each of them would have 1/5 of the data. OpenSearch will then distribute the shards across the data nodes in the cluster. When requests come in, they are processed at the index level, but distributed to the data nodes to actually serve the request. You can see we have 3 shards here: primary 1, replica 1, replica 1, primary 2, replica 2, replica 2, and primary 3, replica 3, and replica 3. So when requests come in, they're going to be sent to some node in the cluster, and that node is going to figure out from a routing table where that traffic needs to go. It will distribute the indexing requests to the primaries. Now I only got one arrow here. It got a little bit confusing with all of the different arrows, but the traffic will go to first the primary. The primary will will index the data and then distribute the traffic to its replicas. So each of the requests that come in, and if a bulk requests include enough documents, it'll go across all of these shards. And in that case, we're multiplying out the work that we need to do across all of the shards in this index. Finally, when the primary has written and the replicas have written and responded to the primary, then the response will come back to the originator, which will send out the response to the client. On the query side, we have a similar multiplication of the work, and we can see the REST APIs coming in. Again, we're going to use the same analyzer on the query itself, on the query terms, so that they will match what's in the index, because those have also been analyzed. It'll come to some node. That node is going to be, again, the coordinator for this request. It checks routing, and it selects one each of the shards for that index. So the primary and one each of the replicas. It doesn't have to be all primaries, can be distributed across primaries and replicas, but this request will multiply out 3 times. So when we're thinking about the processing needs for each of these kinds of requests, they multiply out across the shards and the indices that those requests access. And again, because the shards are the workers, the need here is for CPU, disk, networking, all of these resources to process these requests. As the number of indices that are concurrently accessed increases, we're also increasing the demand, especially for CPU resources. So when you look at the different models of tenancy, bear in mind what is active at any given moment and how that multiplies out across the different nodes in the cluster. And of course, the coordinator node will send out the response once all of the shards respond. So again, keeping this in mind, number one, you want to try to align your shard count and node count. This way, I've drawn it that way in the prior diagrams, not entirely by accident, because this way you have the most even distribution of the work across the nodes in the cluster. You also want to limit your overall shard count. And there are two dimensions of this. The first one is how many shards themselves are on any given node. Each shard is going to take some non-reclaimable space in the JVM, and you don't want to run yourself out of JVM just holding shards. Our guidance is to use a maximum of 25 shards on any node per gigabyte of heap on any node in the cluster. In practical terms, this means that for the largest size heap, we give you half of the RAM goes to the heap, and that caps at 32 gigabytes. 25 shards times 32 gigabytes is 800 total shards. So really no node in any domain or any cluster should have more than that 800. If you're on a smaller heap, do bear in mind that you want to, again, scale that down. So a 16 gig heap, you'd only want 400 shards. The second dimension is looking at the activity that we just talked about. And so if you think about the CPU usage and which indices are active, we recommend that you use 1.5 these CPUs per active shard. A lot of the indices that you have, especially in a log analytics workload, will be idle. These are the ones that are being accessed, right? So in the prior example, I would have 9 active shards, and I would want to have 13 and a half, which obviously would round to say 16 vCPUs in that cluster. So when you are looking at this, and especially in a siloed model, you might want to move your high demand tenants to a different index or a different domain, especially if you're seeing a lot of activity across many indices. Moving high demand tenants to a different domain will help you scale for that tenant specifically and make it a little bit more efficient for you to deploy the cluster. You do want to watch for hotspots, especially around CPU and disk. If you're an EBS-backed instance, you want to take care that your IOPS consumed are not more than the IOPS that you have provisioned. This really is a point, again, to the first point, aligning shard count and node count. If you are unable to align your shard count and node count, you can get uneven usage across the resources in the cluster. And so you want to make sure that you watch out for hotspots. And we'll talk about an operational model that lets you move tenants around with some facility. One of the heavier weight tools that you can use is using custom document routing. When you index a document, or when OpenSearch indexes a document for you, it is randomly distributed between the primary shards. If I have 3 primary shards, every document that comes in is going to be randomly deployed to one of those shards. It's done so based on a hash of an internal ID. You can actually choose to set the ID and route all of the traffic for that ID to a specific shard. This enables you then in the query phase, when you're querying that data, you can specify that same routing ID. Then OpenSearch will send that request, whether it's an indexing request or a query, will go to a single shard. And that minimizes the networking overhead and the access, the scatter gather that generally happens for handling these requests. The flip is that this can cause hot shards where some tenants are randomly co-located together and they happen to be heavier weight tenants. And you want to look at that as the kind of counterexample and makes it more challenging to use. So you really only want to use this when tenancy is very high. Very high is not a well-defined term. I tend to think it has to be in the tens of thousands at least, and possibly up to the hundreds of thousands before you would want to use this very heavyweight tool. So let's have a look at the security and how that interacts with our tenancy model. Amazon OpenSearch Service provides a multi-layer security model. I'm not going to go into great depth around this, but I will point out some of the main features. We have encryption all the way through, so TLS to the endpoint, and then the internal networking, you can enable TLS between the nodes themselves. We also have a sign-in experience if you're using OpenSearch dashboards that can come either from Cognito, your SAML provider, or from OpenSearch Security's plugin itself to provide a sign-in for your users. We have at the edge of the cluster AWS IAM. This is a policy that you put on the domain. Generally, we recommend that this is a pass-through policy that you're going to use Amazon OpenSearch Services security plugin really to provide the fine-grained access control you need, especially in a multi-tenant environment. You best practice deploy into a VPC. And then within OpenSearch itself, we have our security plugin that, again, takes the authenticated user, whether that came in through dashboards with a sign-in or with IAM signed policies or user password. The security plugin will enable you to apply the differential access control for different indices based on your tenancy model. We also support encryption at rest. I'll just mention that with KMS integration that enables you to encrypt your data while it's at rest. So for the fine-grained access control that we provide with the security plugin, you really want to limit your access based on the tenant identity. At the domain level, and if you're siloed or hybrid, you're going to be sending your data to either a single domain per tenant or some set of domains across your tenants. IAM policies, really the most usage there, can allow you to limit domain access based on the tenant's identity if you have IAM request signing that you're using. At an index level, where you're co-locating tenants within that index, then you can provide index access permissions for each of those tenants. And this does require that you have the ability to authenticate those tenants individually. At the document level, whether you're in a hybrid model or a pooled model, the document access permissions you can also do by tenant. So the tenancy enables also within OpenSearch dashboards, we provide a tenancy model that enables you to build within dashboards tenants, public and private visualizations and dashboards. And this is where you can take a particular tenant, say tenant 1, they will have a role assigned to them within the OpenSearch security plugin that enables them to access a particular index. They also have an OpenSearch dashboards tenant within which they can build visualizations and dashboards that are private to themselves. And the access to the visualizations and dashboards is disjoined from the access to the index. So you have to make sure that you provide this tenant the ability to access the data as well as the ability to access the set of dashboards and visualizations. Every tenant, OpenSearch dashboards tenant, has access to a global dashboards tenant where the entire set of users can build visualizations and dashboards that are available for everybody. Similarly, if we have a second tenant, that tenant also needs a role to access the index where their data is. They also have a private tenant for themselves, and they can access the global tenant. Global tenant is also useful when you have some kind of global role where that user needs access across all of the indices, visualizations, and dashboards. So this one would be, for example, a security engineer who needs to be able to look across all of the indices to see what's going on with each of the groups. So we'll talk a little bit about capacity and operationalizing the tenancy models. Again, as I brought out before, when you have different tenants at an index level, they have different usage patterns. And because of the way that OpenSearch distributes the shards across the nodes, you can have scenarios where storage is unbalanced because you have some portion of tenants on different instances. In this case, I'm showing you have a couple of nodes that have 2 big indices or 2 big shards and 3 small shards, and the other ones have 3 or 2 big shards and 2 small ones, right? So you're in a situation here where your storage is going to be unbalanced. As you add more indices and more primary shards for those indices and more replicas, this situation can get very unbalanced. And then the cluster becomes unhealthy. Really, the core of the issue is that the current method for distributing shards is to put shards based on a count of how many shards are on the node. It's more complicated than that, but that's fundamentally, it kind of boils down to it. And so the order that you create the indexes and the sizes of the indexes can result in unbalanced placement. And of course, the storage itself is somewhat of a proxy for the usage, right? So these larger shards are going to presumably see more usage. So your CPU can also become unbalanced based on the usage patterns. To address that situation, you, first of all, as we said in the best practice, you want to set your primary shard count to be evenly divisible by the node count. That gives the best possibility that the shards themselves will get distributed evenly because you're distributing each index evenly across the nodes. Now on the storage side, you can keep shard sizes the same by using the rollover facility. In this way, you change from managing the life cycle of your data based on the time that that data has been there to the size of the indices that you're creating. So it does reduce a little bit your ability to manage directly what's going on with your data. You can't easily remove something based on the time it's been in the domain. But it does give you a very even distribution of that data across the cluster. And that makes it the best shot you got at having an even storage and CPU usage. You can use OpenSearch's index state management to automate the process of lifecycle operations. So I've shown a small policy here that you attach to your indices, and you'll see there's a rollover action that rolls over indices at 40 gigabytes. I can then use the ISM template portion of the policy to attach this policy to all of the logs-star indices in this case. That means that every index that gets created with logs-anything will roll over at 40 gigabyte. And this does, again, shift the lifecycle management from a time-based lifecycle to a size-based lifecycle. On the operational piece, and shout out to NBC Sports Engine, and I encourage everybody to have a look at the reInvent talk that we did together in 2018. You can operationalize your tenancy strategy and really simplify your tenant management by using an external database that holds a pointer for each tenant to where their data is. When your application wants to access that data, it goes to that table to get the assignment of where it is. And that would be a cluster endpoint, an index name, and then a set of flags. When you're, again, accessing that index, when that tenant has data or a query that you want to run, you go to that table, you pull that information, and you route your request that way. The flags are really important because if you add a read-write flag there, then you can actually block writes to that tenant. While writes are blocked, you can then pick that tenant up and reindex their data. You have to have their data set, but you can reindex that data to a completely different location, different cluster, different index, and switch the pointer before enabling write again. This makes it a lot simpler for you to hold the writes off to the side while you're doing that reindexing, so you don't have a synchronization. Well, this is your synchronization mechanism. In this case, the application, when there's an update request, will send it off to a queue, and it'll just spin in that queue until the write flag is enabled again. So wrapping up, we talked about several different strategies and different levels at which you can manage your tenants. We have our siloed strategy, where you are creating a single container for each of those tenants. You have the pooled strategy, where you are creating, you're pooling together some of the tenants at one of these levels. And we have a hybrid strategy where you're using some pooling and some siloing. And if we look at these at the different levels, then we have at the domain level, if you have siloed by domain, then really you're doing traffic routing. These are the methodologies you'll use. You're doing traffic routing based on that tenant's identity. If you're pooling together within a domain, then you're doing an index, a single index where you have multiple tenants, then you're doing that index access. If you have a hybrid or in the pooled as well, you're going to be using a filter field to filter between the different tenants. If your container is a document and you're siloing into the document, right, then you're putting them into either single or multiple indexes. So again, you're using filter field across these different tenancy models. At the pool, if you're pooling stuff into a document, again, you're using a filter field. And if you're hybrid, you're filtering. At the field as a container level, if you're siloed, then you're, again, potentially going by index. You're also using query parameters to direct the query to the particular fields that contain the data. There's some benefits of these different strategies and some trade-offs. So the siloed really gives you independence between your tenants, and that is its strength. It can be easier to scale. It can be easier to move things around. It can be easier just to manage. If it's pooled, then you have one place to go, and that is simpler than a siloed model, and that's its benefit. If you are working in a hybrid model, you have kind of the most flexibility. In many, many cases, in most of the cases for customers that I've worked with, I would say we end up at some flavor of hybrid strategy, because honestly, the siloed becomes a little bit more complex than the pooled, but the pooled is simpler, and the performance characteristics of the pooled model make it simpler to manage the shards level. And so we kind of end up with a hybrid strategy in most cases. I want to thank you very much for your time and attention today, and let us know how it goes with tenancy.